Okay. So our next speaker is, I can already see he's here, Professor David Puelz. He's a principal researcher at Booth School of Business, University of Chicago. He received his PhD in statistics from University of Texas, Austin in 2018. So the title of his presentation is Monotonic Effects of Characteristic on Returns. So Professor Puelz, I'll make you a co-host and you can share your screen.
Awesome, thank you.
So you have about 40 minutes and then 5 minutes for question and answer.
All right, great. Hey, can you guys see my screen?
Yep.
Okay. So thank you guys for having me. This is a fun talk to give. It's, was part of my graduate school research, and I changed the title slightly, although I'm going to be talking about the same thing. My current title is machine learning useful for modeling the cross-section of returns? So let me give me 1 second here. Make sure that and this is joint work with Jared Fisher, who I went to graduate school with, and my PhD advisor at UT Carlos. Okay, so I just wanted to kind of start off the talk by showing you guys a picture of what our data looks like. So if you were to just take a look at this plot, and I've removed the axis labels purposefully, if you were to just kind of, flip open a book, look at this plot, you might say, oh, this looks like a trace plot, maybe from a Bayesian MCMC. Maybe I took some draws from a couple of normal distributions and kind of plotted them cross-sectionally maybe. But it turns out that this data is monthly stock return data. Okay, so what I have here is I have each dot represents a firm or a company, and the x-axis represents the past performance of a company, something that we call momentum. So you can think of, the left-hand side of the x-axis are, let's call them the past losers. So these are firms that have not done well in the past. And then towards the right-hand side of the x-axis, we have the past winners. Okay, so these are firms that have done well in the past. And I kind of, change the size of the dots based on how close to January 1978 I am. So I'm kind of plotting all these panels on top of each other. And then, of course, on the y-axis, we have the monthly return for a particular company and a particular momentum value of that company. And what has been done for a long time in finance is, we have these particular characteristics that we can observe for a company, and we want to understand the relationship. Okay, so what is the relationship between return and a company's past performance? And we can see that this data is very, very noisy, right? Any kind of complicated model, any kind of machine learning model, we have to be very careful about when we try to fit it with this data. Okay, so this picture will be kind of foreshadowing the future obstacles that we might encounter when we try to fit a model with this data. So what are we trying to do? Well, with this observed data, we would like to figure out which characteristics that I can observe for a particular company are predictive of its return. And there are two parts to the answer to this question. One is going to be more of a predictive question, a predictive part, right? We'd like to build the right Bayesian model, and I'm a trained Bayesian statistician, and so we're going to kind of focus on a Bayesian formulation of a model. But the second thing is, we have actually many of these observed characteristics. So For our particular data set, we have about 40 characteristics for every single company, and these characteristics change over time. Now, I think the most recent updated version of the data set contains hundreds of characteristics. So when we want to think about telling a story, we need to have some kind of selection procedure to tell us which of these characteristics are most important. Okay, so these are going to be kind of broadly the two components of the talk. What are we actually after very specifically? Well, we would like to model this conditional expectation function of stock returns. Okay, so let's define RIT as the excess return of firm I at time t. And then X is going to be this vector of characteristics of a firm at a particular point in time. And we would like to figure out what this F is. We'd like to learn F. We'd like to learn its form, and we want to kind of, fit it in such a way that it's accurately describing this conditional expectation function surface. And the goal is we're going to, put in characteristics for the previous time. Okay, so for the previous month, since we have monthly data. So our first goal is to learn F, but then of course, we would also like to figure out which of these X's matter, because X in our particular case is going to be a fairly big vector. So here on this slide, this is one particular way to learn F, or to build a model for F. And it's been a very common way in past finance studies. So this is a famous paper from the Journal of Finance back in 2001, where Jagadish and Tipman started to study this thing called the momentum effect. And what they did was they said, okay, to try and figure out how momentum is describing a firm's stock return, let's sort all of our firms in our panel based off of their momentum value. Okay, so momentum is how well the firm did in the past. And then let's compute the average return in, say, each of these deciles of this sorted characteristic. So if we take a look at the top left of this table, for example, we see that the first decile, if we look at all stocks, 1965 to 1998, the average return is 1.65. The second decile is a bit smaller, at 1.39. And then we go all the way down to the 10th decile. So these are firms that did not do well in the past, and we see that they have a low return. And then if we look across different time periods, we see a similar trend. Past winners do well, and past losers don't do well. And so one thing I want to note here is that there is this very interesting monotonic relationship between the momentum of a company and its future return. And it turns out for many of these characteristics, this type of monotonicity, where I have kind of a monotonicity on a particular variable X that I observe for a company, is fairly prevalent in finance. And when we're building our model for F, we would like to take advantage of it, not only for more kind of theoretical finance reasons, but also for statistical reasons. Okay, so this is just a picture of what I was just describing, right? So kind of a visualization of the table on the previous slide. So the type of data that we have, you can think of these dots as the same dots that I showed on the first slide. Each represents a company. And we see that here, this particular characteristic, as I look at the return of the stock, the return increases as this characteristic increases. And what I'm doing is I'm basically, when I do portfolio sorting, is I'm fitting a step function to this data set, the step function being the red lines. And so the first question is, well, are these portfolio sorts, are they useful statistically, particularly when I have high dimensional data? And the answer is that they become pretty cumbersome. So these are, specifically the challenges from a statistical perspective when I start to think about modeling a larger and larger panel. The first one is, the one that I've been hitting on a few times. X, our vector of characteristics, is multidimensional, and often it's going to be quite large for a finance data set. And there's also there's no information sharing across the X space when I'm doing portfolio sorts, right? What I have to do is I have to do these portfolio sorts in kind of a let's call it a marginal way, or where I take a particular X, I split it up into deciles, and then I take means within each decile. And if I were to try and incorporate any kind of interactions across the X space, that'd be very difficult, right? Because then very quickly I start to only have maybe one stock return within a decile of a decile of a decile of 3 X's. So the way that we're going to get over this is we propose modeling the conditional expectation function using quadratic splines, and we are going to incorporate what we think are 2 very important features to kind of capture or to describe this data. One of them is going to be monotonicity constraints, and the other one is going to be time variation. And so here I've kind of written out the form of that model, right? We're going to separate our X's into each separate additive function. And then each of these functions are going to have monotonicity constraints if we believe that the returns should be monotonic in that particular X. Okay. So these are the 2 features of the model that we propose. And what we'll see is that these features are going to lead to very interesting improvements over very complicated machine learning models. In particular, we see that the monotonicity over the partial effects, that's going to really help us not fit to the noise in the data, which we've seen is very, very noisy. And then, of course, we expect there to be time dynamics, right? This is a data set that is changing over time. And so how each of the characteristics, how each of those X's describe the return should change over time. And we'd like to capture those time dynamics. Okay, so here's again kind of a visualization of why we might want these features for our model. So here I'm showing you 2 of the estimated functions from our model with and without monotonicity, without being on the left-hand side, with being on the right-hand side. And these are the same axes that we've been looking at. So the x-axis is momentum, how well a firm did in the past. The y-axis is the expected return. And we see that if we don't incorporate monotonicity, these quadratic splines tend to be very noisy, right? And this is partially a feature of quadratic splines, but we could also imagine that if we were to feed this into some black box machine learning model, that it also might kind of learn these wiggly, noisy relationships. So the functional fit on the left is something that I don't believe at all is a true functional form, right? But the functional fit on the right, I could definitely believe that this more truly represents the relationship between momentum and return. And what's nice is that with these monotonicity constraints, we're better able to kind of navigate the bias variance trade-off of this problem. Okay, and so why would we also want dynamics? Well, here I'm showing you the same 2 functional fits, the same axes, but now these are different points in time. So the function on the left is the momentum fit at January 1978. So this is the momentum partial effect function, January 1978. And then we look at the same function, but now in January 2014, and we see that this momentum partial effect function is starting to flatten out. So this is kind of indicative of, you know, momentum potentially going away as we move through time. And what's nice is that these types of dynamics are things that our model are able to capture. Okay, so you know, that was the, you know, kind of super brief high level summary of our model. What I'd really like to focus on now is kind of the second piece, is more of the inferential part of this case study. And that is, well, we have this model. It seems to fit the data relatively well. We can incorporate monotonicity constraints on X's that we believe should have those constraints. And so what this leaves us is with a very complicated posterior for F, right? Where we have, you know, spline coefficients, we have non-inclusion parameters because we have some shrinkage going on. Everything is time varying as well. So what in the heck do we do with this model? Okay. To put differently, how do we understand which of these characteristics within this vector X matter most for the conditional expectation function, or for the return surface? And so the way that we're going to do that is we're going to do something that I've been working on for quite a while, and it kind of has started more in the Bayesian variable selection literature, and it's called posterior summarization. And the main idea is that we should do selection after fitting the model, not during the model fitting process. So to put differently, and what I would like to advocate for is to say, you know, characteristic selection is really a decision problem. Therefore, we should use an appropriate loss function, not necessarily a more cleverly designed shrinkage prior. So what this means is that we're actually going to first fit our model is a step one, which we've already done. We've seen the model fits. And then after the inference is taken, or has finished, we're going to compare models or sets of characteristics based on this utility function or loss function. Okay, so a couple brief slides on how this posterior summarization procedure that we propose works. There are three components. So first, let's define B sub t as a model decision. So you can think of this at a particular point in time as the set of characteristics that I'm using in my model. We're going to let lambda t be a complexity parameter. You can think of lambda as similar to the lambda in a lasso type regression. Theta t is all of my other model parameters, which we have quite a lot here for the spline model. And we're going to let r tilde sub t be my future data. Okay, so this is the data that I'm able to generate from my posterior predictive. And there are three components. The first component is the loss function. Okay, so this measures the loss, or measures the utility for a particular model decision. And the second component is my future data, r tilde sub t. And then the second component is my complexity function. This measures how sparse my decision is. So you can think of low complexity as a small number of characteristics describing the expected return surface. Large complexity as a large number of characteristics using essentially all of my data. And then of course we have the statistical model, right, which is going to characterize the statistical uncertainty. And then there are three steps to posterior summarization, which I'll briefly outline here. The first step is the usual decision theoretic step. I'm going to compute the expected loss, where this expectation is over all unknowns, right? So this is the joint posterior and predictive distribution, right? I have future data, I have model parameters, and I want to optimize this expected loss. And then I'm going to look at what I call the regret. This is basically the loss for a sparse decision for a simple model versus the full complicated model. So how much am I losing from a loss perspective, when I look at my sparse model, which I've now indexed by lambda sub t, versus the full model. And what's nice and what's crucial about this particular variable selection procedure, different than any other selection approach, is that this regret, right, which is just a difference in loss, is a random variable whose distribution is induced by the distribution of r tilde sub t. Okay, so now we have access to these random variables, and what we do is we can look at graphical summaries of these random variables. So in particular, we can look at, I call this a satisfaction probability. This is just the difference in loss between my sparse model and my full model, right? And so the higher this probability, the closer my sparse model is to my full model. Okay, so a lot of math, some steps in there. What's the output? Well, the output are these things called posterior summary plots. So you can think of a posterior summary plot like a lasso solution path, right? Where I'm kind of looking at sparse models and it kind of gradually goes up to denser and denser models. You can think of it as a lasso solution path, but now I have predictive uncertainty bands around each of my sparse models. So what's nice is that if we look at the left-hand figure, for example, I'm plotting the distributions of the delta random variable for the number of predictors. So as I have more and more predictors, more and more characteristics in my model, my delta gets closer and closer to zero. We see that, after around, say, 17 predictors, my sparse model is really no different than my full model up to predictive uncertainty. Okay, so this is why this predictive uncertainty is very important and why we kind of advocate for this particular approach to variable selection. Okay, so this is how we're going to think about selecting characteristics for the model. Now, with all of that said, I'd like to show you guys some results. So what data are we actually using? Well, we are focusing on a data set that is from a review of financial studies paper from one of my colleagues at Booth, Michael Weber. And it's a really interesting and rich data set. It's all of the monthly stock returns from most US traded firms. So you can think of about 2,000 to 3,000 firms each month. And then for each of these firms, for every month, we have 36 characteristics. Okay, so you can think of these characteristics as being size, book to market, momentum, how well did the firm do in the past, its leverage, various accounting measures. And we have this data for a pretty long time period, from 62 to 2014. And to build our model, what we then did is we said, okay, for each of these 36 characteristics, we're going to go back in the finance literature and we're going to see whether or not there is theoretical evidence for a direction of monotonicity. So just a couple of examples there. We can think of, the Fama and French factors as all having, kind of hinting at a direction of monotonicity. We can think of size, for example. All right, so Fama and French said that small firms tend to outperform large firms. So that's a statement of monotonicity for the size of a company relative to the company's expected return. And so we do this for all of the different 36 characteristics. We see whether or not there is theoretical justification for including monotonicity in our model. And then we fit our model and we start looking at some of the output. Okay, so here is a slide that I have here showing the dynamics of a couple estimated functions for some different time periods throughout our data set. The first one is size. Okay, so we can think of the x-axis as being the size metric. Okay, so on the left-hand side, I have small firms. On the right-hand side, I have big firms. And then the y-axis is going to be the expected return. And we see that we do generally see this relationship between the size of the firm and the firm's expected return. We have small firms tend to have larger returns. Large firms tend to have smaller returns. But this is not always the case, right? So you know, this relationship is, you know, kind of moderated, you know, throughout the 80s, and then in the 2000s, 2005, 2010, it actually becomes fairly strong. Compare this with two other characteristics. Here we look at profitability and leverage. We see the profitability really doesn't have an effect conditional on all of the other characteristics. Right, this is kind of relatively flat, and its partial effect function is basically just being shifted by the intercept in our model over time. If we look at leverage, leverage seems to not have an effect for the first couple time periods, but then has a stronger effect as we move further and further through our sample. And by the way, leverage was one of the characteristics where we did not have a monotonicity constraint, and we see that it has kind of this interesting behavior in 2005 and 2010. So one quick thing that I wanted to note here is that our model is able to tell us about these relationships between characteristics and the expected return conditionally, which I think is really, really important, right? Because, you know, what's typically done and how folks have usually looked at the return characteristic relationship is just marginal on each x, but really we would like to put all of the x's into our model and make a conditional statement on size relative to return, right? So it might be the case that marginally profitability does have an effect, but when I look at the partial effect function within the full model, it doesn't have an effect at all, right? So this profitability effect is probably being described by a separate characteristic within those 36. Okay. A couple more interesting pictures. So here I have one of the other 36 characteristics. This is called short-term reversal. So you can think of this as actually the opposite of momentum. So it turns out over shorter time periods, very short time periods, there's actually a reversal effect that one sees in the data, meaning that short-term losers tend to be short-term winners, right? Okay, so firms that have done poorly in the past over a short time horizon tend to do well very quickly after. And this is something that we see. So this is the partial effect function now plotted over time. So this is kind of the return surface that we get out of our model. And we see that for sure, past losers on a shorter term scale tend to be past winners, right? By these kind of, you know, this green tail on kind of the lower decile of that characteristic. But then past winners, right? This tail effect on the other side seems to be going away as I move further and further through my data. I get closer and closer to present day. The plot on the left is again looking at the size characteristic, and we see that this too also is definitely changing over time, and we see that really the size characteristic is driven largely by small firms, right? So we see that small firms tend to have very large expected returns, conditional on all the other characteristics. The large firms during various periods tend to have smaller returns, but otherwise this is, you know, a relatively flat surface as we look at the upper percentiles of size. And so all of this stuff is kind of interesting, right? Because now we're kind of looking at these X's, these characteristics in the context of many other observable X's. And then of course, these are two characteristics which don't really have much of an effect at all. So you can think about profitability and investment. These are, you know, kind of two new factors that Fama French proposed, I think maybe back in 2015. So, you know, they moved from kind of a 3-factor model to a 5-factor model. We see that these additional 2 factors, conditional on all of the other X's, don't really seem to have much of an effect. Okay, so this is very important information as we kind of, you know, think about the you know, the factor zoo, and, you know, people proposing that all of these characteristics matter. And so this is something that for sure we found very interesting that came out of our model. Okay, and then so now we've looked at how these characteristics vary, and we'd like to make a statement about selection, right? Okay, so what I have here is I have a kind of full plot of all 36 characteristics. They're functional fits for a particular point in time, and I'd like to say that these 5 matter most for describing the conditional expectation function. So how do I do that? Well, we're going to use posterior summarization. If we run our posterior summarization procedure over time, what we see is that we have a very interesting relationship in terms of which of the characteristics are selected. So here I show a heat map. I have all 36 characteristics on the vertical axis, time on the horizontal axis, and each one of my little black dots represents that characteristic being selected in the selected model for that particular point in time. And we see that volatility, momentum, book to market, size, all of these characteristics up here in kind of the upper right tend to be selected often, right? But this is not the same over time, right? You know, we see that, okay, you know, for some time periods we have relatively sparse models where this SUV, which is standard unexplained volatility, is selected, and then, you know, for other periods we have relatively dense models. But what's nice is that because we have these dynamics, we can kind of see how this set of selected characteristics, selected through posterior summarization, changes over time. And then this is kind of one of my last slides that I think really gets at the let's call it meaning of the title of the talk. How do other machine learning methods do relative to our monotonic splines model? So this is something that was very important for us to look at because we felt very strongly that as there were many folks in finance that were focused on, you know, fitting the kind of best, most state-of-the-art machine learning model to this data, we thought that might be a bad idea because the data is so noisy. And so what we did is we fit a variety of what we believe are the best competitors to our spline model from the statistical machine learning literature, random forests and Bayesian additive regression trees, BART. And we wanted to compare, or we wanted to see how our model did relative to those models. So here what I'm showing are 2 different metrics, and I typically don't like to show tables and talks, but I think this one is pretty informative. We have 2 metrics. We have something we call an out of sample R squared. You can think of this as kind of let's call it a measure of out of sample predictability. And the metric can be negative. And then we also have a Sharpe ratio for a particular portfolio. So let's first look at the out of sample R squared. Here we have different window sizes for the different columns. So this is just how much data I use. And then we have all of our models. So our spline 0 model, that means that I did not use any monotonicity constraints. Spline 6 means I used 6 monotonicity constraints, and they were the monotonic relationships that we felt had most support from the finance literature. Okay, so you can think about, size, momentum, so on and so forth. And then Splines 24 is using 24 monotonic constraints. So this is using all of the monotonic constraints that we were able to find support for in the finance literature. And the main takeaway from the left-hand side of this table is that, splines do pretty darn well. And they actually have performance somewhere in between random forest and BART. And what's nice, and I think what's even more compelling, is that our spline model is completely interpretable versus BART, which is kind of a black box model where I'm combining trees together. I have really no way of figuring out what the BART expected return surface looks like, right? So this is kind of purely a predictive model. Yes, do you have a question?
I'm sorry, that was a noise from somewhere.
Oh, no, that's okay. It's okay. Okay, so we see that splines is somewhere in between two very competitive machine learning methods, both of which are very difficult to interpret. And then let's look over at panel B. So panel B is something I call the Sharpe ratio. What type of portfolio this is for each period of time, I get return forecasts from my model, and then I go long the top decile companies based off of return forecasts, and I go short the bottom decile companies based off of return forecasts. And then I do this over time, and I compute the Sharpe ratio of that portfolio. That's why these Sharpe ratios are very, very big. And we can think of this as kind of a more economically meaningful metric. And we see that the splines do very, very well. And they're basically competitive to BART, which we view as probably one of the best statistical machine learning methods out there. And so this is not, and we don't like to think of it necessarily as a horse race as much of a statement that you just have to be really careful when you're using these complicated machine learning models for finance data, because since it's so noisy, we've learned, and we've tried to kind of display in this paper that structure is very, very important, right? You need some amount of bias and structure in order to have a successful model, and so that's kind of the main takeaway of this slide. Okay, so I think I have a couple minutes left, so I'll conclude, and then I'd be happy to answer questions. A couple big thoughts are first related to posterior summarization. Loss functions we view should be used for the variable selection step in lieu of any kind of complicated sparsity inducing prior, right? So what we really advocate for is we would like the selection to take place after the statistical inference has been done, and that's really from a decision theoretic perspective, and we call that method posterior summarization. And then of course, when we go through posterior summarization, we're using our statistical uncertainty as a guide to kind of protect against the overfitting of a particular model. So, you know, you can think back to that slide where I have my lasso-like solution path and the predictive uncertainty bands around each of my sparse models. And then, yeah, then of course, you know, the other thought that I didn't put on the slide is that, you know, you just have to be really careful about using default machine learning in finance. That's something that, you know, we've always kind of known, and this was a fun paper to write in that respect, because we were able to, you know, put kind of a more kind of rigorous statistical argument behind that. And yeah, and so then I have here 3 papers that are kind of related to the posterior summarization, and then also, of course, the paper on the monotonic spline model, which recently appeared in the Annals of Applied Statistics. Thank you guys all for spending time listening, and I'm happy to answer any questions you have.
Thank you so much. Great